Hello. When we last took a look at our little Boombot, we had it moving. We had the little buttons on the side. We were able to read them. And I challenged you to go out and have it drive a pattern. And I was looking for you to complete something maybe a little bit like this. So here we go. The Boombot's sitting there. Now, it's just waiting for somebody to come along and push one of the buttons. And I can never remember which side the buttons are on. So there, I finally figured it out. And it is. There we go. Push the button. It's off. There we go. Then a turn to the left, goes out, does that 4 times, comes back and stops. Then I talked to you a little bit about the challenges in making it go forwards and backwards. Now, that's with the drive motor batteries running. You can also turn the drive motor batteries off. And we've got these 4 LEDs down at the front that are really useful. So if you're just using logic level or you're trying to figure things out on your desk and get your coding watching going, on mine they're blue and they're red. Okay, on mine when those 2 red ones come on, it goes forward and you can see the blue and the red blinking on and off. There they are dim. There they are dim again. So the dim is slow, and when one of them changes direction, that's turning happening in there. So when I set it up and when I let it go here, um, oh yeah, I got to remember to turn the motor batteries back on again. And when the motor batteries are on and the logic batteries and it's booted up and you press the button and there it goes off. And so those lights will be flashing while it's driving around. And then it comes back here, moves forward slowly and backwards slowly. And I challenge you to take a look at how to make it move forwards and backwards slowly. So let's just well, now you know what YouTube thinks I want to watch. Apparently, I'm interested in the world's largest lemon battery. Strangely, I'm not. Okay, I've got some code back here that we're going to take a look at, and those of you in my TTED 5060 class are probably familiar with the DP Scope SE. We're going to use an oscilloscope that we made as a kit to show well, basically what's going on and why it's moving forwards and backwards. And we'll talk a little bit about how to get it to move backwards slowly as well as to move forward slowly. And then we'll wrap that all up into one big drive function so that we can get the driving out of our way when it comes time to using our other sensors. And we can have real simple, straightforward commands telling our robot how to go forward, how to go backwards, how to turn left and right, and travel at different speeds. So having a good drive code is pretty useful for what we're going to be doing. Okay, so anyway, let me all that out of there, and let's take a look at our Boombot. And there it is sitting there. And I'm just going to pop the top right in here. We took a look at the schematic a little bit last time around. And this board underneath here connects the various pins on our Arduino to the various pins on the L293D chip. Right down underneath here, this is our motor driver chip. And that's what's going to make our robot work for us and do our thing. Let me just adjust these windows around for a second. There we go. And now you should be able to get a little better view of what I'm about to do for hooking things up. So as I was going to say, there's this thing called a DP scope. And it's basically a small USB oscilloscope. So you might have, actually at your disposal, you might have a full-on oscilloscope. But these are a neat little kit made by a really friendly and helpful guy. And I should also mention that you can purchase an inexpensive surface mount version of this kit. Let me just pull up the web page and show you where you can get one. There we go. If you don't have access to a scope, you can find one at Abra, A-B-R-A, electronics.com. And what you're looking for is the OSC001 PCB scope. And let me just see if I can shrink that so it all fits on one screen and you can see all the details on there. And retails for about 34 bucks Canadian. So pretty good deal, actually. It's slightly less expensive than actually making the kit. About the same actually, but involves less work. And it's a neat little device, plugs into a breadboard, and you can hook your test leads up onto it. And you can check out the specs on that. Obviously, it's not going to do everything that a multi-thousand-dollar Tektronix scope does, but you know, for most of the stuff we're doing on this little robot, it's just fine for showing what's going on. So if you don't have a DP scope, you can go online and you can just buy one of these. They're a neat little device. And they actually work with the same software, so everything we're doing right here should work for you if you've got one of those scopes. Alrighty, now when we hook up our scope, we need ground and a couple of references. We're going to take a look at the signals going to the left-hand drive motor right here, because when we drive our robot, that was the one that I reversed to make it turn right. This one just kept driving forward all the time, and to make it turn, I spun this one into reverse, causing it to turn that way. So we'll see more interesting signals if we just look at one side for right now. Now, in order to see that, we need some connection points on the board, and this is something I might improve if I do another version of the board. There's not a lot of test points to jump in and do investigations on here. So if you take your ground lead, now let me bring it in right here. On my board, the ground lead's coming off channel 1 and it's black. We've got these neat little pins on it right there. So those little pins can come in, and we want to hook that up to ground because that's black, obviously. And right up here at the front where I've got the ultrasonic rangefinder plugged in, if you look carefully at your board in there, and let me see if I can get this out of light, you can see it says GND right in there. Okay, close enough. You'll see where I'm plugging it in anyway right now. And I'm just going to hook it around this pin. Try not to hit anything else right on there. There we go. Now we've got a ground reference for our entire board. Now your channel 1 lead that we're going to hook up is going to come down here now. It's a little hard to see because it's tucked away underneath the Arduino right in here, but if I hold it at just the right angle, you can kind of see in there that we've got a resistor sitting right in here. And that resistor, if I hook up to this side of the resistor, I can never remember if that's Arduino pin 6 or Arduino pin 7, but I'm on there right now. Okay, you can look at the schematic for that, and you can know that for sure. Just make sure that's hooked right up on there. Now, the reason I'm able to use that particular resistor is because the resistor then leads to these two LEDs. And those two LEDs, and this is my channel 2 test probe, and I don't have the fancy hooks on it, which is okay, because it's going to come down and it's going to connect right here. So what I'm going to be able to see as we run the oscilloscope is relative to the ground voltage, I'm going to be able to see a real-time graph of the pin on the signal pin coming in to drive this side and the signal pin coming in to drive this side of our L293D chip. Now, if you think about that in terms of driving your tethered mini sumo robot or something like that, a project that we do a little prior to that, basically I'm looking to see whether your thumb is pushing up on the board or your thumb is pushing down on the board, but we're doing it electronically, so it's going to happen a lot faster, and yeah, those electrons are a little smaller than your thumb, so they're going to be harder to see. So I'm going to take this pin and put it right down on here. Okay, now before I do that, I have to set the DP scope up to be ready to receive the data. So get your DP scope software ready over here. And because this is going to run for a little while, okay, because it takes it a while to go out and do that sequence, the first thing I'm going to do is I'm going to switch my DP scope software over to data logger mode. And that's going to let me log data right across the screen right here. And basically it's going to give me 0.5 seconds per division, but it's only going to take 20 samples per second. So it's not going to be a high resolution picture, but it'll give you a quick overview of what's going on. And then we can take a look at the fine detail of what's happening a little bit more closely later on. Now, we don't want to observe the logic channels. It's not going to hurt if you have that turned on, but you can turn that off. And let's just do a test run right here. And you should see data starting to scroll across your screen right now. And if you touch something on one of your probes like this, you should see it looking weird. We're just going to stop that and we're going to clear it. Okay, so now we're pretty much ready to go. We've got the DP scope set up. I've set things up. I'm going to drop that down to 1 volt per division and 1 volt per division on each side because this is a 5 volt board and we've got more than enough voltage here. And so I'm going to run this. It's going to start going along, and I'm going to make sure I've got this held onto the input pin right there, because that's connected back directly to my Arduino. Again, take a look at the schematic. It's in the electronics assembly instructions, and in the previous video I talked more about that when we're talking about how to get the motors to run. And here we go, I'm going to run it. Now, right now, you can see that both are at 0 because that's our rest state, our halt state. You'll notice that I've got the motor battery turned off. So let me just move this up a little bit so you can see what's going on. The motor battery is turned off. The logic is turned on because it's getting power from the USB pin right back here, but you could be running it just off your main logic battery. And so with the motor battery turned off, I shouldn't be expecting things to go anywhere. I've set my code up so that it will run that pre-programmed sequence when I push a button. And here we go. Okay, there we go. It is running that pre-programmed sequence. And there's the slow forward and backwards. And I'm going to stop it right there so we can take a look at a little bit of what just happened in there. Okay, so you'll recall from the video that the robot started out driving forward. And here you can see that one of the signal pins went high and the blue signal line stayed low. Okay, and those don't necessarily correspond to the LEDs. I'd have to go back and look at the video in more detail. It'd be really cool if they did, but I have no idea if they do or not. 50% chance, I guess. Anyways, to make it go forward, the red line came high right in here, and the blue line stayed low. So that was telling the L293D, the motor driver chip, to put a positive voltage on one side of the motor and ground, okay, or the negative voltage, the low voltage on the other side of the motor. Now, to get it to turn, I had to briefly reverse the direction of this motor right here. If I wanted to turn the other direction, I would have briefly reversed the direction of this motor, and we'd be taking a look at that motor. But here you can see this is where we briefly reverse the motor. And right up here, you can see that now the blue is the high. Okay, so the other pin has gone high, the other pin's gone low, so we've changed the direction of flow of current through that motor, and for this brief period in here, it's spinning backwards. Okay, and actually if well, I know I set it for 300 milliseconds, and if I look at the code right here, it's 0.5 seconds per division, and yeah, that's not quite one full division on there. That makes sense. Then I have it go forward for a second. That's about 2 divisions right in there. And again, you can see the direction changes. And this is another corner right here because we've swapped directions of the lead pins. So the motor changes direction. And then we come over here, and then I send the command to stop it. Both motors rest for a second, and there we go. And now in here you see something interesting because you see a whole bunch of choppy stuff going on with one of the pins. Now, keep in mind that we've got 2 pins driving the motor, and only one of them can be a PWM output. Only one of them we can use the analog write command with. And you'll also recall that the analog write command isn't really an analog write so much as it is a pulse width modulated simulation of having an analog write. And so it's turning a pin on and off really, really fast. Now, this doesn't show it, okay, very well at all. You can see a little bit of it turning on and off. But I want to take a look at this because in the big picture, you can see that we start with this pin high right here. And there's little segments right in here where the red is high and the blue is high. Well, your motor's not going to turn if it's got high voltage on both leads. In order for your motor to turn, you need to have a voltage drop across the motor. You need to have high on this side, low on this side, so your motor turns in one direction, or high on this side and low on this side, so your motor turns in the other direction. Okay, so in this situation where they're both low, well, 0 voltage this side, 0 voltage that side, it's not turning. In this situation where they're both high, 0 volts on that side, 0 volts on that side, they're not turning. Now, again, this section was happening so fast. Those pulses on and off were coming in at about 1,000 times per second. And we are only taking 20 samples a second, so we need to be able to see this in a bit more detail. So I'm going to clear this off and I'm going to set it back to oscilloscope mode now. And I need to be a little quicker on my finger to do this. And I'm going to come in here and I'm going to change it down so that we've got 1 millisecond per division. So we can see at millisecond resolution, it's going to take 10,000 samples per second. We should be able to get a much neater view of what's going on the robot. We just won't be able to capture as much time on the screen. Okay, so let me set that up. Let me hit run right over here. Okay, we start off and both of them are at 0, so the motor shouldn't be running. Okay, and here we go, high, low. Goes by really briefly when it goes low, and I've got to be ready to stop it right in there. Oh, I was just a little bit late. Okay, well here you can see the situation where it should be running in reverse. Notice that the red line is low right in here. So this is what a slow reverse looks like. Because right now, the only time it should be running in reverse is when we have differences between the blue line and the red line. So in here, the analog write command is automatically turning the direction, sorry, the PWM pin on and off really rapidly. And in this case, I think I've got it set to a 50% duty cycle, but we can change it to different duty cycles as well. And you can see here that while it's on right here, we've got this line up here, and then it turns off briefly, but it's turning on and off so fast that it looks like the motor's just turning slowly. So this is where it's running, let me see, with the red line on the bottom, that's running in reverse. Let's see if we can capture it running forward this time. Okay, here we go. Set this back to run again. And go, there we go, forward. Back. You can see brief moments of backwards. And then we pause. And this is where it's running backwards. So in here, you can see that we've got the red at the top. And now it turns on for these segments where it's the bottom with that turning backwards. So that's how we're getting partial speed coming to our motor. Now, because if you understand that, that's great. You can skip ahead through the next little bit because I've got a few things that are based upon this, and this little bit of how the analog write command works can get a little bit confusing. I'm just going to take a look at it on a piece of paper and go over it one more time here. Okay, I think I've got the screen set up properly there. So here's some of the things that were going on. Now, the way this is set up inside the Arduino is that we've got two pins controlling the motor, and I've named one of them the direction pin and one of them the PWM pin because the PWM pin can do that analog write thing, and the direction pin is just the one that we're using to tell us what it's doing. Now, most of the time, you're going to be running at full speed, so you're essentially sending digital write commands, not analog write commands. Analog write 255 is the same as digital write high, okay? Because that means it's on all the time. So digital write right in here, PWM comma high, is going to set our red line right up here. Our red line is the PWM pin. And digital write dir comma low is going to set our direction pin low. So now what we're doing is we're sending a signal where we're saying, well, we want this output to be high and this output to be low. So we will have a voltage drop across here, and the motor will start turning around in that direction. And that direction, if we've set everything up, should be forward. Okay, now if we come down here and we take the same pins, but we reverse their setting. So instead of high and low, we go low and high. Now you can see the blue line right up here is up at the top. It's at 5 volts. This one's down at 0 volts. So when that goes through our speed controller, the outputs are going to be high, going to this side of the motor, and low going to that side of the motor. And now you're going to have power running in the opposite direction, and your motor is going to spin in the opposite direction. We'll call that reverse. Okay, so it's pretty simple when you're just dealing with full speed forward and full speed backwards. It's a little more complex when it comes time to be part speed forward or part speed backwards. Okay, now let's take a look at that because we'll zoom in and you'll remember you'll seeing that pattern. There was some interesting little spikes on it and all that that we can talk about a bit later on. But now here we're using an analog write command to the PWM pin, okay, and we're setting it to 200, which is going to give us a slow forward command because we've set digital write to low. So what we do right in here is when we come along and we see that the red is high and the blue is low, well, that's the same as we have right up here where the red is high and the blue is low. So for this fraction of time right in here, the motor looks exactly like it's 100% on. Okay, then briefly in here, because of the analog write command not staying on all the time, this is the pulse width modulation. Each of these is a pulse, and what determines how long they stay on for is the width of the pulse, okay? So this comes down and it spends a little while in the off position. Well, now our red and our blue lines are both down at 0 volts, so our outputs from the speed controller on both sides are also at 0 volts. That makes the motor go off. We come over here, this side gets automatically turned back on by the Arduino because that's what the pulse width modulation does. And now the motor's on for a little bit and it's off for a little bit. And this is happening well, actually about 1,000 times a second. Okay, so this is great. This gives us a slow forward command. Now, something interesting happens if I just change the direction pin. Okay, because you'd think that if you just change the direction pin, then if I had slow forward before, now I should have slow reverse. But it doesn't quite work that way, okay? Because now we're using the same number for the analog write pin, okay? So our PWM pin is still getting this signal. So it's got the same pattern coming in here in red, okay? Now, that's perfectly fine. But where that's a bit of an issue is that because now we've changed the state of the direction pin. When we were running slow forward, if the direction pin was high, the motor was on, if the analog write, the pulse width pin was high, and of course we've set the direction pin to be low, then the motor's on while the analog write pin is high. But in here, the motor is off when the analog write pin is high because the direction pin is also high. And in this state, we're putting 5 volts to both sides of the motor. And it's coming in there and the 5 volts is pushing this way and the 5 volts is pushing this way. There's nowhere for it to go. You need to have 5 on one side and 0 on the other in order for the electricity to flow through. Or more technically, like 4 and 1 on one side. You need a voltage drop across the motor. Giving them both the same voltage isn't going to help you out very much. So what happens on here is that the only time the motor turns on now, it does move in reverse. Okay, that's a good thing. But the only time it's doing it is during what was previously the off period. So while 200 in forward slowed us down a little bit, 200 in reverse slows us down a lot. Because most of the time, this signal is high, this signal is always high, so the two cancel each other out and the motor's off. The only time you have anything on is during this time where they're a little bit different. So if you want this to work properly, okay, and you want your speed to be the same, okay, when you send a when you reverse the direction, so if you want 200 forward and 200 backwards to be the same speed, you need to change or basically invert the sequence of ons and offs that you get from your analog write command. Well, how do you do that? Well, at 128, which would be right in the middle, it wouldn't make any difference, okay, because it would be on 50% of the time and off 50% of the time. But down here, we weren't at 128. So what's the opposite of 200? Well, 128 and 128 add up to 256. Okay, we know that 255 is our biggest value. So what I'm going to do is I'm going to say, well, if this number plus 200 adds up to 255, that's probably going to be the opposite value right in there. You know, because 0 is the opposite of 255, 128 is the opposite of 128. I'm going to put 55 in here because that is 255 minus 200. Okay, so that's the 200 setting that I want. Okay, but because I've changed the direction, I can't just punch 200 in because if I did 200, then it would be super slow because I've changed my direction. So when I reverse, I need to come up with the byte inverse, you might call it, okay, because we're dealing with a byte number. What's the inverse of a number in byte? Okay, it's whatever you need to add up to get there. That's going to equal 55. So I'm putting 55 in here, the equivalent of 255 minus 200. And now, if you take a look at this one, okay, what we'll see in here is this pin will only be high for a little bit. Well, that's good because when it's low, the motor will be on because the direction pin is already high. But just like we have right up here, okay, when the direction pin is high and the PWM pin is low, this situation right here, the motor will be on and spinning in reverse. Comes right over here and both of them go high. Now you got that situation where you've got 5 volts on each side of the motor. It can't do anything. The motor turns off. Come over here and it turns on again. So now we've got the motor on for this segment in here, but turning in reverse, and on for this segment in here, but turning in reverse. Whereas when we use 200 and we get it going forward, it's on for this period and on for this period. So now we should get about the same speed from each of the motors. So that's all set up to explain one little thing that happens in the drive routine later on. And if you don't actually, understand what the PWM is doing, then you're going to see this one command in the drive line, in the drive code that makes no sense to you whatsoever. Okay, let's take a look at the code and I'll show you how I've got my code set up because we're going to want a function to make it really easy to do our driving so that we can just tell the robot how we want it to drive and we don't have to do all this math time and time and time again. Okay, so just going to adjust these screens here. And here we go again. This should, oh, just a minute. I got to hit the magic transition button there. Now you can see what I want you to see on here. We've got our notes over here where we just explain things. We've got our DP scope software a little lower down there where you can see the red and the blue lines that I was illustrating on here. Let's take a look at how I go about doing this in code. Okay, now this starts off very much the same way that your last code did, where we define some constants for the pins, but now you'll see I've added something in here. I've added motor left reversed and motor right reversed. Okay, now this is why when you're building the robot, I say I don't care which side of the motor you solder up to which pin on the connectors that you're plugging into the board. Okay, really doesn't matter. We fix it in software really easily, and we just put this configuration in right here. And if it's -1, okay, then your motor will spin in the opposite direction. And if it's +1, your motor will spin in the normal direction, whatever opposite and normal are. There's probably some big debate going on in the motor that anyway. So here we've got the same thing set up for the right side of the motor. And we've got the motor right reversed and setting right in here. So on mine, my left motor was reversed, so I set it to -1, and my right motor wasn't, so I set it to 1. Don't set that to 0 or else your motor won't move. You'll see why 1 and -1 matter later on. But basically, the pin positions are exactly the same. I've even put something in here for motor number 3 because I'm pretty anxious to use the Disc-O-Matic cannon, but we're not there yet, so just hang on. Now, I've also defined a few terms in here. Okay, and again, anything that's not going to change in the program, I use the const int terminology. Sometimes you'll see people also use the hashtag define for that. It's just another format to say the same thing, that you're telling the compiler anywhere where it sees the word forward, use the number 255. And you can see I've used my comments in here to say that setting the speed to 255 means full forward on that motor. Okay, and full speed reverse is minus 255. So a positive for forward, a negative for reverse, and a range of speeds from 0 to 255, because 255 is the biggest number you can put into a byte variable. I've also got one in here for halt. Okay, now that's a bit redundant, and obviously 0 means stop, but you can't use the word stop. The Arduino already has assigned the word stop to mean something important, so if you try to redefine it, it's going to give you an error. In the last video, we also took a look at the right and the left-hand LEDs attached to pins 9 and 13, and we took a look at the button pin and how to read the buttons on pin A2. And in my comments, I've left some notes in here on how all that works, because quite frankly, I'll be doing this project for a couple of years and I'm going to forget everything over the summer. So it's really good to have notes and comments set inside here to help you out. And sometimes I find it helps other people understand your code a little bit better too. Okay, I've got some variables that I'm going to use in the program. Count is something that we don't need right now. Actually, I shouldn't even have joy X and joy Y in there. Those are for something coming up where we use the joystick to drive things around. We'll take a look at that in a future video. And our button variable, I think we might have used that in the last one as well. I've also got an integer variable for our left motor and for our right motor. Okay, those are what I'm going to use to pass some numbers off to the subroutine that manages all this. May as well turn on the serial output ports. Right now, I don't have any debugging information to print from here, but if you need to print anything out, you could. Setting your pin modes, really important. Okay, if you don't set your motors to be outputs, particularly the direction pins, you're going to have a problem. And again, there's motor 3. You're not quite ready to be firing discs off of here yet, but I've got it in there anyway, because yes, I was firing discs with it earlier. Okay, just didn't delete everything. So let's take a look in here, and we're going to set our LEDs, and we're going to run a little test on them at the beginning. And I really like these little boot up tests where you just flash your lights just a little bit so that you know, oh, the Arduino on there rebooted. My robot's booting up right now. And then this bracket down here to indicate that we've come to the end of our void setup. Oh, nice. It tells me what that's hooked up to right up there. Okay, here's our loop command. And this is where you can see where I've maybe done my code a little differently than you have. Okay, now the first thing I've got in here is a little statement that does absolutely nothing until one of the 4 buttons is pressed. Okay, you'll recall that when none of the buttons are pressed, we actually read 0 on that analog read pin. Okay, we only start to see voltages on that button pin when buttons are pushed. So long as the analog read on there is less than 10, maybe you use the number 11, maybe you use 20, maybe you use 5. I didn't use while it equals 0 in case there was some random fluctuation on there. You know, you get a weird reading and it kicks out of the wait function on here. Give yourself a little bit of margin of error on there. We're waiting for a button to be pressed, and if a button's pressed, it's definitely going to be higher than 10. Okay, so this comes along, and normally we'd have some squiggly brackets in here and some commands and that going on after a while statement, but you can actually get away with it. And if you only have one command, you can tuck it right in here. Actually, I should have just hit Control Z because I ended up with more stuff in there than I wanted. Go away. All right. Now, down here, I've got a for statement. Okay, and the for statement, really useful. You recall it where just take any variable. This is what I set the counting variable for, to count from 1 through 4. And it's an integer type variable, so I started at 0. And this will keep doing it so long as it is at less than 4. And each time it comes around, it's going to increment by 1. And each time it goes around, it will do the things between this bracket and its matched bracket right down here. Okay, so everything in this sequence is going to repeat 4 times. Now, I say drive forward, forward. So when we've got everything configured properly, that should make the robot go forward on both sides. Okay, that should send a value of 255, 255 to our drive routine. And we'll take a look at the drive routine in just a minute. Now, once I start moving forward, I need to wait for a little bit. Okay, now right now, we're still doing fairly simple code, so we'll use a delay. Later on, we'll take a look at better ways to make the robot wait for a little bit. Delay is what we call a blocking function, and nothing else can happen while that delay is happening in there. So generally, we try to avoid delays, but when you're just starting out, they put the delay command in there for a reason, so use it. Okay, and then it took me a little bit of experimentation to figure out that on my robot with my batteries, turning for 300 milliseconds was just about the right amount of time to execute a 90-degree turn. It wasn't perfect, but it was pretty close. Okay, so what the robot's going to do is it's going to drive forward for 1,000 milliseconds for 1 second. Then I'm going to reverse the left-hand motor, causing the left-hand motor to spin backwards and the robot to turn this way, which you just saw in the video. Okay, and that's going to happen for 300 milliseconds. And as soon as it finishes that, it's going to come around here. Okay, it's going to increment the count. So I started at 0, count's going to go up to 1, and it's going to say, yep, 1's less than 4. It's going to do it again. Count will be at 2. That's left 3. And then it'll come up here and count will finally be equal to 4, and it'll say count, no, 4 is not less than 4. It'll kick out of this loop, and it'll come down here after executing this command 4 times. It'll send the drive halt halt command, and motor stop. Take your breath for a second. Okay, literally 1,000 milliseconds. And now you can see in here, this is drive forward at half speed. Excuse me. Drive forward at half speed for 1 second. Drive backwards at half speed because 128 is half of half of 255, and then delay for 1,000, and then halt. And then because this is a void loop, it goes back and does it all over again. But the first thing it does is it waits for that button to be pushed so you're not chasing your robot all over the floor by something scootering all over the place. That's probably looking pretty compact. If you haven't written robot code before, most of the robots, VEX robots, FIRST robots, almost every educational high school robot has some variation of the drive command, and they put some number in here, and usually a 1 will mean forward and a -1 will mean backwards, or a 100% will mean forward and a -100% will mean backwards. It doesn't make that big of a deal exactly what they're doing. In our case, we're using 255 because that works nice with the 1 byte PWM function. We could use 1 and then we could just say, well, okay, 0.5 is 128. But then you have to get into floating point numbers, and the Arduino doesn't like them all that much. Okay, anyway, so that's what's running along there. Now, each time it sees the word drive, okay, well, the Arduino doesn't know what drive means, okay? We have to tell it what drive means. And this is where we come down here, and this is our drive routine. And if you're a student in my class, I'll share the code with you. Otherwise, you'll have to convince me that you're a teacher. But you can, retype this code if you're watching this and doing this in somebody else's class. Okay, now what we've got right in here is this is how we define a function, okay? Now in this case, we're starting off with a void command. Okay, and you'll notice we've got void setup and void loop. And what the void means is that this function that we're doing is going to do something. It's got a role to play, otherwise we wouldn't have it here, but it's not returning a value. Okay, if it were to return a value, so it might return an integer value or a floating point value, or maybe it would even return two different values, usually just one. Um, so what would happen if it was returning a value, we'd say what type of value it was returning. This one's just going to do something for us. It's not going to go out and do any math and return a value for us. So we're just going to say void. Okay, now drive is the name of the command right in here. And in here, it tells it what variables to expect to be passed from the program. And so I've called them left speed and right speed. They're both integer type variables. So works great. You know, you could get it, you could actually make them, no, I couldn't quite make them byte variables because we're using minus 255 and plus 255. Arduino handles integer values just fine, so we're using it anyways. And then the first thing that we do when we come in here, and this is something you wouldn't necessarily do unless you'd screwed up a lot of code in the course of your life, and believe me, I qualify in that category. The first thing I'm going to do is I'm going to check for minimum and maximum values. Because if I try to write a value higher than 255 into the analog write function, there's not a way that it can handle that. I might get some weird results. And they'd be really hard to troubleshoot because by the time I was doing that, I'd be deeply buried into the program. So as you're going through and as you're developing your software, it's nice to think about, well, how could I screw up? Where could the errors be? And can I trap them and control for them right now? And an error like trying to send 258 to your motor, we can trap right here, or sending minus 258. So that's all this is doing right here. It's taking a look. Left speed is the number that's being passed to this function from the program. And forward is, in our case, 255. So if the number passed to us from the program is greater than our maximum speed, then we just reassign the number that's been passed from the program to be our maximum speed. So basically, if it tells me to go 258 and I can only go 255, change that speed so I'm only going 255. Don't try to break any rules. In fact, one of the ways hackers get into a lot of systems is by going through and finding out something that doesn't have proper error checking and then injecting errors into the code that cause it to break apart. I'm not necessarily expecting the government of China to be trying to hack my Boombot code here. Russia, maybe, but not China. Okay, let's take a look down here, and if left speed's left than reverse, here we check for errors in the opposite direction as well, and there we go. Okay, now you'll recall at the beginning of the program, and pardon my high-speed scroll, right up here, we had these two commands, motor left reversed and motor right reversed. So if one of your motors is spinning in the wrong direction with this code, just change this from -1 to 1, or from 1 to -1, and it'll spin in the opposite direction. Okay, now what we do with that is all the way down here, is we account for the motors that are installed backwards. And basically, we just multiply the value that's coming in by that value. So if your motor is hooked up normally and it's spinning forwards when it's supposed to spin forwards, you multiply by 1. In other words, you don't multiply at all. And if it's supposed to spin in the opposite direction, well, how do we make something go in the opposite direction? We just set it to the negative so it spins the other way around. You multiply by -1. Okay, so that's a really quick way to account for, did I solder this side of the motor to this pin, or did I solder this side of the motor to this pin? Doesn't really matter how you soldered it, you just change that one number up at the beginning of your code, and this will multiply by that number and automatically correct for that. Okay, so now we've got a few different conditions that could be happening in here, and this probably isn't the optimal way to write the code, but I do think it's a way that it's easy for people to understand what's going on here. So we're going to take a look at the left motor first, and this section of code right in here, as you can see, all deals with the left motor. Set the pins for the left motor. So there's three possible states that the left motor could be in. Spinning forwards with a speed greater than 0, spinning backwards with a speed less than 0, or stopped with a speed exactly equal to 0. Okay, so if the left speed is greater than 0, then this is going to be forward, and at least we're calling it forward. It should work out to be the equivalent of forward by the time all the pluses and the minuses are added up, multiplied up. And we're going to analog right. So this is where we set that pulse width pin of the left speed, and we're going to set the motor left direction pin to low. Okay. Now, if the left speed's less than 0 and it's turning backwards, okay, we're setting the motor left direction pin to high. Now, the whole part of the beginning of the video where we took a look at this sheet right over here, okay, and we took a look at the DP scope down there, was all to explain this one little line right in here, where I say 255 plus left speed. Now, first of all, keep in mind this command will only be executed if the left speed is less than 0. In other words, if it's a negative number. And when you add a negative number, that's the same as subtracting that. So in our example over here, where I said, okay, if I'm trying to get 200 when I go forward, what do I want 55 when I go backwards? Well, negative 200 will come in here. It will trigger this part of the routine, and our pulse width modulation will end up giving us 255 plus negative 200, which will give us that 55 so that it'll move slowly backwards. Yeah, okay. I hope that made sense. If not, time for that rewind button. Maybe there are some advantages to having online recorded lectures. If you watch that a couple times and you're not getting it, then bring it into class next time. We've got a lab and we'll go over it. All right, and finally, the real easy one. If they both equal 0, if left speed equals 0, then you've sent the halt command and we're going to stop it. You're going to set both pins low and the motor's just going to sit there and do absolutely nothing for us. Technically, I could have set both pins high. That would also stop the motor, but low seems to be a more normal state for that. And then this, is just wrapping up the conditions right there. We do the same three things for the right side of the program, and that's all done. And we come up here and we return to the program. And so each time we do a drive command, we send different numbers. Oh, excuse me. We send different numbers right down here to this drive feature, and this drive program runs through, does it all for us. And now, when you're trying to control your robot, you don't have to think about, do I add 128 or do I subtract 255? How do I make it go forward slowly? How do I make it go forward backwards? You've just got to think, what do I want the motors to do? And you've got a drive function that takes care of all that for you. So anyway, I'll put this code up on the Learning Hub for my students at BCIT. And if you're doing this, for some other strange sadistic reason, you've probably seen enough of it that you can get it all into your computer and make it work. You've probably already skipped ahead to that part and have already written something a little bit more efficient and compact than this. Try this and see how your robot goes. You might have to play around with the positive one and the minus one for your motors at the beginning. I'm going to be showing you some more code in the next little while that is built upon this drive routine. So I think it's important that you understand how that drive routine works. Alrighty, thank you very much, and good luck with your Boombot. We're working our way towards that cannon.